Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous lecture we were discussing the dimension reduction techniques and specifically principal component analysis. In the previous lecture we applied principal component analysis on breakfast cereals database and two particular variables, that is energy and customer rating. So now today's lecture will start with applying principal component analysis on almost all the variables that are available in the data set. So as we talked about in the previous lecture, that will include all numerical variables except two, which are mainly having zero values in almost all the cells. So we will eliminate them. So generally different brands try to indicate that these two these two particular variables, trans fatty acids and cholesterol, are zero in their product, so that they can market them much better. So that is why that information has been recorded, but essentially because most of the values are zero, that is not useful for us. So let's select the appropriate data frame. So now if you want to look at the selected variables again, the PCA2 is the new data frame that we have subsetted. So you can see the variables, almost all the variables that were originally available in the data sets have been taken for principal component analysis, right, starting from price, energy, protein, carbohydrate, sugar, dietary fiber, fat, saturated fatty acids, and then monounsaturated fatty acids, polyunsaturated fatty acids, sodium, iron, and last one the customer rating. So let's apply principal component analysis. The PR comp is the function, again we are going to use it. So let's execute this particular code. Now let's look at the summary. Now so you would see that 13 principal components have been used. If we look at the number of variables that we had in this new data frame on which we applied principal component analysis, if we count the number of variables, we can apply names function as well. So 13 were there. So now 13 original variables were there, and now we have 13 principal components. Now let's look at the different values that we got after applying principal component analysis. So first PC1, if you see the proportion of variance, it's 68%, and the second principal component is 29%. So if you combine these two, 68 and 29, it's almost almost I think 97%. So these two principal components, PC1 and PC2, almost contributing 97% of the variability that was there by the original variables. So we can eliminate other principal components. So only these two principal components are capturing the most of the variabilities. Therefore the dimension can be reduced from 13 to 2 because of the most of the variability being captured by these two variables. Other principal components, if we see that the amount the variability that proportion of variance that they capture is less than 3%. PC3 is 2.8, and then others are insignificant, totally insignificant. So first two, we can have first two principal components as two dimensions, and therefore we would be able to reduce the dimensionality from the 13 to 2. So let's look at other values. So let's look at the rotation weights. So these are the weights. Let's look at the nicer version of this. So we'll have a look at just three decimal values So now let's look at the first principal component PC1. So let's see which original variables are contributing to PC1. You would see that price, that is minus 0.99. So first principal component is mainly determined by price, and other original variables, they are contributing to insignificant amounts. If we look at the second principal component, then it is you can look at the second value. This is energy, minus 0.968. So second principal component main contribution is coming from energy. So PC1 is essentially, we can say, price plus kind of variable, and PC2 is energy plus kind of variable. So most of the variability being captured by price and energy. If you try to make sense of it, you would see generally Indian consumers when they buy breakfast cereals, they generally, we might have this perception that they generally go for price and energy. Same is being reflected in a way here. So other principal components, so proportional variance, they explained, was anyway quite less, and then so it doesn't make much sense to look at the contribution of original variables to these principal components. So PC1, PC2, it's like price plus and energy plus. So let's move forward. Now what is the problem here? In this case, there is one problem that is there in this analysis that we applied. So if we look at the variables that we are talking about, its price, that is measured in rupees, then the energy, then that is being measured in calories, then protein and carbohydrate and other contents, they are being measured in grams and milligrams, right. So if you look at, we are having different measuring units. So still the data that was fed to principal component analysis, that was not normalized. So maybe that was the reason we had just two principal components dominating most of the variability. So let's apply principal component analysis after normalizing all the numerical variables under study. So let's run another principal component analysis. So again, this time we are going to use the same data frame, that is DF PCA2, and now you would see scaling is being done. So scaling, second argument is scaling is true in the function. Now this, let's execute this. Let's look at the results. Now these results are after doing normalization. So normalization is something that we have talked about in the previous lectures. We talked about that sometimes some variables, because of the scales, they can dominate the results, they can influence the results, and which might not be desirable in most of the scenarios. So therefore normalization is the one recommended step before going ahead with the building of your model or running your model. So now this particular results that we see, they are after doing normalization. Now if you look at the proportion of variance, now we see PC1, 50% of the variance is being captured by PC1, 16.5 is captured by PC2, 10.3 is captured by PC3. You can see much bigger role for PC3. You can see even bigger role by PC4, also 7.5%. Similarly PC5 6%. You can see PC6 4%, PC7 3%, and after that. So you can see that first seven principal components, they are capturing more than 90% of the variability and most of the variability in the original variable. So now the dimensionality which we thought when we ran principal component analysis without doing normalization, we thought it was reducing from 13 to 2, but that was not the actual case. If we do normalization, if we do scaling, then we find out that it is actually from 13 to 7. So we would still be requiring 7 new dimensions to capture most of the variability. Let's look at the weights of new principal components. So let's look at the nicer version 3 decimal points, up to 3 decimal points. Let's start with the first principal component. In the first principal component, if you see, the largest contribution is coming from energy, and then that is not the only dominant dominant contribution. You would see the similar numbers: protein, carbohydrate, dietary fiber, fat, and the other things also contributing in a similar fashion, right. So this is how PC1 is being determined. And if you look at the PC2, then sugar is dominating this particular component, 52 contribution coming from sugar. Then if you look at another other numbers, you would see sodium is also there. Even sodium is bigger than sodium's number is bigger than sugars. So sodium, sugar, and then the iron. So these are dominating the PC2. Similarly, if we look at PC3, then the biggest weight that we can see is coming from price, that is minus 0.79, and then after that much smaller weights after that, and we can see that minus 0.31, that is again coming from sugar in principal component 3. So if we look at the principal component 1, the weights are also with minus sign, right. So therefore energy and protein, so this is mainly signifying PC1 is mainly signifying the particular principal components which is determined by energy, protein, carbohydrate, fat, saturated fatty acids. So many of these contents, right. PC2, we see that it is mainly determined by sugar and sodium. If we look at the PC3, it is mainly determined by price. So PC3 could be called price plus, PC2 is mainly can be called sugar and sodium, sugar and sodium. PC1 is can be, we can term it as health plus. So these could be the new names for these different principal components, these different new dimensions. And since we require first 7 principal components, so similarly we will have to do a similar exercise for other principal components as well. Now let's what we'll do, I will plot the new dimension that we have just computed. So let's look at principal component 1 and principal component 2. Let's go back to the results that we had earlier. The proportion of variance. The proportion of variance by PC1 and PC2 is 50 and 16.5. So let's plot these two dimensions, and then we can compare it with the original plotting that we had done earlier. Let's look at the range of particular variables. Minus 6.96 to 3.02. So you can see appropriately x limit has been specified. Let's look at the range for the second variable, and you would see that minus 4.14 to 1.49. You can see the appropriately the y limits have been specified. Let's change the margin and character expansion through Pyre function, and let's plot. Now let's zoom to this particular plot. The marker point has been chosen as the small. We have chosen a smaller marker for generating this plot. Now you would see these are the points for Z1 and Z2. So quite different from the case that we had earlier, right, when we applied principal component analysis on energy and customer rating. we saw a distribution redistribution happening from 87 13 to 90 and 10, and and that was also without normalization. Now if we do normalize, we can see this kind of scenario. Now variability that is being captured by just these two dimensions is slightly less in comparison to previous two models that we developed. If we want to further analyze this information, we can label all these points. We can label all these points by their product name. So we can make a we can analyze these new dimensions further. Now, so these are all the points have been labeled by their product names. So now we want to further analyze. Right, for example, if as we move along in the Z1 direction, and if we look at the weights that were actually contributing for this particular directions. So let's look at the PC1. So this was the PC1, and so as we move along to the Z1 direction from left to right, the energy content would actually decrease, right. So you would see that as we move along from left to right, the energy content would actually decrease, and then the protein would also decrease. Similarly, other carbohydrate, fiber. So all these. So as we move along from left to right, so probably less healthier options are more clubbed on the righter side of this particular plot. So this is how we can analyze. Similarly, for the second directions also, we can make similar kind of analysis. For example, sugar and sodium, they dominated. Sugar, sodium and iron, they dominated the second direction, second principal component. So as we move from bottom to top in this direction, Z2 dimensions, we would see that there is decrease in these three contents, that is sugar, sodium and iron. So therefore more healthy cereals would slightly be in the mid section, and then left mid section, right. So that is where probably more healthier options are there. So let's go back to our discussions. Now if we look at the principal component analysis, how it could be used in the data mining process. So how we can actually apply principal component analysis in our data mining modeling and reduce the dimensions to lesser numbers. So first step is going to be applying PCA to the training partition. So we'll have training partition, validation partition and test partition. So first step would be to apply PCA to the training partition. So now we'll have new predictors, and they will be would now be different principal score columns. They would be new predictors. So the original variables we will not be using further, and new score columns that we just saw through that mod $x value, right. Similarly, for all the principal components, we can find new values, and they are going to be new predictors. So as we have been talking about, we'll have new names for also a new name for them as well. For example, we were talking about health plus, price plus, energy plus kind of new variables for new principal score columns. So now once we have new predictors, we are ready to build our model on training partition. But how do we evaluate our model? So for that, we would be requiring validation data set and test data set. So the principal weights that we obtained while we applied PCA to the training partition, the same principal weights can be applied, can be used to compute the variables, new variables from the validation partition. So, the validation partition, we can apply the weights that we computed from applying PCA to training partition can be used to obtain new scores, and then these new predictors can be used to perform to actually test the model and then refine it and then test on new partition, that is test partition. Now, we look further at PCA. What we have been doing is in PCA is we mainly focused on numerical variables. So, we generally selected all the numerical variables and then we applied PCA on them, and then we looked and analyzed the results to find out how many new predictors we will have and whether the dimensions are going to come down or not. So, those are the things that we looked at. But if we look at the way PCA is done, we don't generally exploit the relationship between predictors and output variables. So, that relationship is generally ignored. So, that is one limitation of this principal component analysis. So, this particular limitation can be overcome using some other methods. So, limitation of principal component analysis, that it does not include the relationship between predictors and the outcome variable, that can be overcome using some other methods. So, these are so we come to our next category for dimension reduction techniques, that is data mining techniques. So, some of the data mining techniques that we would be covering in more detail in the coming lectures, they can also be used to reduce the dimensions. So, first one that we are going to discuss briefly is regression model. So, we can apply some of the subset selection procedures using regression models. So, for example, linear regression for prediction tasks. So, for prediction tasks we can apply a linear regression. So, therein using the using the significance of the coefficient that we get for different variables, right. We can find out which are the important variables, and therefore, we can get rid of the insignificant variables and also variables probably having a low coefficient value. So, we can also if the we can also drop some of the values if the coefficient value is on the lower side. So, those variables can also be dropped even if that is significant. So, now domain knowledge is also important. Sometimes even though the coefficient value is on the lower side, the variable might be of more importance, but if that is not the case, probably we can drop those variables also. So, we can drop insignificant variables and some of the significant variables which are carrying low value. So, that is how subset selection procedures of regression models can be applied. Linear regression, different subset selection methods that we will be covering in coming lectures can be run to find out the best subset which is able to explain the model or fit the data. For classification tasks, we can apply logistic regression, and the same process can be adopted there as well. So, we can use you can find out the significant relationships, and then we can also have a look at the coefficient values, and thereby we can determine which variables to drop, and thereby we can reduce the dimensions. We can also look at which regression models the subset are explaining most of the variance that we can do through multiple R square values. Regression model can also be used for combining categories. So, we can use p values to actually find out that if there are few categories for which we have which are insignificant, right. If there is a category which is insignificant, it can actually be combined with the reference category. It can be combined with the reference category, and this category can be eliminated. If we have two category which are having similar coefficient, similar value right, similar coefficient value, they have similar influence on the outcome variable or output variable, then those variables, those category can also be combined. So much can be done after analyzing the results. Another technique that can be used for dimension detection is classification and regression tree. So in a coming session, we will discuss classification and regression tree in more detail, but to give you an idea that there is under this technique, we develop a classification tree for classification task, and we develop a regression tree for prediction task. So while we build this model using different using pool of variables, a large number of variables, the end result is going to be a tree diagram. So which would be representing, which would be giving us the different classification rules or prediction values, and will also be incorporating the important variables that were used to build that particular tree. So if a variable doesn't show up in that particular tree diagram, doesn't figure in that particular tree diagram, that means that particular variable can directly be eliminated. So that is how dimension can also be reduced. So we can start from a large number of predictors, and then some of them can actually be eliminated if they don't figure in the tree diagram. Similarly, in the classification and in the classification tree as well, we can combine categories if there is similar kind of if they are coming in the same branch, and there is possibility of having similar classification rules for both of them, then probably we can combine them. Similarly, for regression tree as well, if a particular variable is not coming up in the regression tree diagram, then also those variables can be eliminated from the analysis. So more detail on these two techniques, regression models, whether it is linear regression or logistic regression, and how they can be used for how subset selection procedures can be developed using these models, and how classification and regression tree card can be used for this model for dimension detection. We will discuss these when we come to the lectures where we discuss these particular techniques. Now, one difference between principal component analysis and these models, regression models and classification and regression tree, is that these models they account for the relationship between the predictors and the outcome variable. So whether it's a regression model, that the way linear regression is modeled, it's the relationship between outcome variable and the predictors that is actually incorporated in the modeling process. Similarly, for logistic regression also, the predictors and the outcome variable, their relationship is incorporated, and any subset selection procedures that are used later on, they are based on those relationships. So that being one big difference. Similarly, in classification and regression tree also, while we develop the tree diagram, it is the relationship between the variables that help us reach to the terminal nodes or leaf nodes and do our classification and prediction. Therefore, it is the underlying relationship between those variables that is also playing its role in determining the importance of variables. So we will stop here, and in the next section we'll discuss the performance matrix. So thank you.